Hello, and welcome back to Technology Now, a weekly show from Hewlett Packard Enterprise where we take what's happening in the world and explore how it's changing the way organizations are using technology. We're your hosts, Aubrey Lovell
and Michael Bird. Right, so in this episode, we are looking at the very cutting edge of computer technology and how it could change the way we look at artificial intelligence and IT. We are examining the world of novel accelerators in AI, which in some ways does exactly what it says. It's a new way of accelerating problem solving in AI. But you won't be surprised to hear it's a whole lot more complicated than that. In fact, it's a whole new way of looking at computers.
Indeed. Curious? Well, we are too. So if you're the kind of person who needs to know why what's going on in the world matters to your organization, you know this podcast is for you. And if you haven't yet, subscribe to your podcast app of choice so you don't miss out. All right, Michael, let's get into it.
Let's do it.
Okay, so we know that generative AI and machine learning has been an absolute game changer. And in just the last few years, we've entered a world in which technology can help us do the legwork of discovering new drugs and materials, make us more sustainable, and accurately communicate and break down problems for humans to understand. Now, according to findings by Bloomberg, there is an astonishing 40% compound annual growth rate for the AI industry at large. And we've linked to that report in the show notes.
But with all that AI has achieved, it does have its limits. There are certain kinds of mathematical problems that an AI just isn't very good at solving. In particular, ones where there might not be an answer. So computers like to take an instruction and give a definitive output. And if they can't do that, well, the system kind of falls over and breaks down. These questions, known as brutally hard problems in the AI space, require new and extremely innovative ways of thinking. But if we nail them, or just get close enough to an answer, it could create a second wave of AI transformation.
Now, we could try and explain these problems, how to overcome them and why they matter, but today's guest is way more qualified than us. Happy to introduce Ray Beausoleil. He is a physicist, senior fellow, and senior vice president at HPE, and he leads the large-scale integrated photonics lab at Hewlett Packard Labs. Hi, Ray. So let's start by outlining what these brutally hard problems are when it comes to AI. Does that phrase have a specific meaning?
There's a mathematical and computer science class of problems called NP hard, non-polynomial hard. And without getting into the mathematics, what they really say is that these are problems that we can show are in this class of problems, where you either cannot prove that a solution that you find is in fact the ultimate solution, or you can't predict in advance whether or not you can solve that problem. However, when I put it like that, it makes it sound solving these problems is hopeless. But in fact, it isn't. What's really going on is mathematicians, bless their hearts, are trying to tell us that this is a class of problems where the corner cases might never be solved in the age of the universe, or that you show me a proposed solution for one of these problems and you cannot prove to me that in fact that's absolutely the solution. However, this is why accelerators are relevant. And this is really, really important. There either are relevant cases that are of interest to us at human scale, where we can find either answers that we know are correct, or where the answers are good enough that we can use them to be productive, to move society forward. And a really good example of a problem like that is called the traveling salesman problem. The idea is that, let's say there are a certain number of cities, and there's a salesperson who is going to try to efficiently go from one city to another city with the minimum distance possible. And the constraint is you can only go to each city one time. So that's a constrained combinatorial optimization problem. Now, if you draw 3 cities on a piece of paper, you can solve that problem in your head with a pencil. It's really easy. And you can prove that that's the best answer. But what happens is, as you go from 3 to 10 to 100 to 10,000, you not only can't solve it by hand anymore because there's a gigantic, exponentially large number of possible routes. So you don't have a prayer of solving it with a pen and paper, but you also can't prove if you draw a picture. You can certainly draw a connecting map, but you can't prove that, in fact, that's the solution. But the great thing about that problem is there is a heuristic that works incredibly well. So, in fact, if you go online and you look for traveling salesman problem in the US, that heuristic has been applied to draw a connectivity diagram for all the non-trivially sized towns and cities in the US. That is actually quite good, that you could actually use in a practical way to go to every significant city in the US. But you can't prove that that, in fact, is the best one. But we don't care. Because what really matters to you is that you can come up with, in relevant, interesting circumstances, come up with a solution that's good enough. And that may be enough to help us design new life-saving drugs. It might be enough to help us solve climate change. And that's the motivation.
Right. In that context, what is an accelerator?
The simplest way to understand an accelerator is to start by understanding the way we build computers today. We build them in a particular way, originally due to John von Neumann, where we have memory and then computing, a CPU, and the central processor unit stores data in memory, reads data from memory, but then does its computation separately from that memory. And that von Neumann architecture is ancient. And so it's been around for an extremely long time. And unfortunately, there are classes of problems where that's an extremely bad way to think about how to solve them. What an accelerator does is it uses a different kind of architecture to attempt to speed up a critical numerical or logical path that allows you to solve these certain classes of problems faster. And the accelerator, frankly, that you know already and you use all the time is a GPU, a graphical processing unit, that essentially started, it was originally designed to assist with ray tracing and graphics on your computer monitor. But then over the course of time, a lot of numerical experts worked together to figure out a way to speed up the kind of mathematics, matrix vector computations that are used in order to, for example, train a neural network. And so the question is, can we think of a different way to architect computers that makes it faster or more efficient or more accurate to solve some of these other problems that are of tremendous interest in the world and in particular to HPE's customers?
So, what does a novel accelerator actually do? Like, how do you architect a computer that can generate answers to these problems, and also how it can be analyzed?
So, here's a very concrete way. And this one is what's called a seedling. It's a 1-year program that is designed to come up with an accelerator that can more rapidly and more energy efficiently train neural networks. And so it does kind of the same thing that a GPU does, except it does it with data in an optical format. And it takes advantage of a unique property of light. And that's the fact that different wavelengths don't interfere with each other. And that's why the fiber optic network is so efficient and works so well. But then weirdly, the same wavelengths, identical wavelengths, interfere with each other. And so on the one hand, there's no coherence between different wavelengths, but there is coherence between the same wavelength. And you have, if you've ever taken a pebble and thrown it into a calm pond, you know exactly what that looks like, right? You drop a pebble into a pond and you see waves form. You drop 2 pebbles into a pond and what happens? There are places where the waves run into each other. And in some cases, those waves are twice as high as they would be if there was only 1 pebble, or twice as deep, or calm and flat. And so that coherence we take advantage of on a chip, where we're building integrated photonics, waveguides that are so tiny that you can't see them without, well, a scanning electron microscope is the easiest way to do it. Under some circumstances, you can use a microscope, but they're much tinier than a human hair. And light is propagating down them. And we can get light of the same colors to interfere. We can get light of different colors to pass through each other. And we use that to very efficiently do what a GPU does. And so that's an example of harnessing light to build an accelerator to make the mathematics more efficient of training a neural network. So that's one example. We have another program that's a 4-year program that is really directed towards solving some of these extraordinarily different problems. And it completely breaks the von Neumann architecture by doing the computation in the memory. And so what happens, it's wild. Instead of having separate compute and memory, you store the data in the memory and then use the transistors in the memory cells to actually do the computation on the data in the memory. The idea is that certain classes of very difficult problems, like binary satisfiability problems, could be solved much more efficiently in these in-memory computing systems. But what's interesting is we wanted to solve a particular class of problems, and we started out designing a photonic computer that could do it. And we kept looking at these problems and we thought, wait a minute, there's this disadvantage, there's that disadvantage. And so we eventually realized that we were designing a photonic in-memory computer. And we realized that there would be a more efficient way to do that if we used electronics. And so we developed this brand new architecture. It's been around for a while. We didn't invent it, but we realized the electronic version of that computer was the one we needed to build. And so we partnered with a couple of universities and a small company in order to bring this program together. But again, it's not something that we would be able to do if we were still yoked to that von Neumann CPU memory computer architecture.
Absolutely fascinating. Thanks so much, Ray. And you've got such a skill for explaining incredibly complicated concepts. So thank you for sharing it with us.
Yes.
All right, we'll be right back with Ray in a moment, so don't go anywhere.
Right, it is time for Today I Learned, the part of the show where we take a look at something happening in the world that we think you should know about. Aubrey, it's your turn this week. What do you have?
I have quite a good one this week, Michael, and I promise it's going somewhere, so just bear with me here. But do you like the promise of clean, cheap energy?
Oh, absolutely.
And my follow-up question is, do you like mayonnaise?
I would say I am somewhat indifferent to mayonnaise, sort of take it or leave it. Why do you ask?
Well, because we have a marriage like no other. And it turns out that mayo could be a key to the future success of fusion power. Super weird,
right.
But let's just hear me out. Let's bear through this. Okay. Researchers from a university in Pennsylvania in the US have found that mayonnaise shares strikingly similar properties to certain states of plasma in fusion reactors, giving a rare opportunity to test fusion dynamics in the physical world without having to rely on HPC simulations or scarce access to real fusion reactors. This is so crazy. It all comes down to something called Rayleigh-Taylor instability. In one of the common fusion reactions called inertial confinement, capsules filled with isotopes of hydrogen are rapidly heated. And these capsules melt to form plasma, which is then contained and controlled, hopefully to release energy. But it's not a perfect process and can cause instabilities as the different materials and energies react. So, mayonnaise, Michael, does the same thing, apparently. So, using a special rotating wheel filled with a plasma substitute, the team found it's possible to create slow-motion versions of what's going on in a reactor and watch the various stages and phases that plasma goes through without the need to actually undergo fusion or reach temperatures of millions of degrees. So clearly, this isn't a substitute technology, but being able to view these processes happening in a slowed-down state is surprisingly useful. So you'll never look at a sandwich the same way again. Their findings were also published in the journal Physical Review E, which we've linked to in the comments. Who knew mayo would be so important?
Who? It is so important. It's so important to all of our lives. Anyway, thanks, Aubrey. I am genuinely speechless. Right, now it is time to return to our guest, Ray Beausoleil, to talk about novel accelerators in AI. And Ray, I'm going to dive straight in with a question. So, Ray, this might be a bit of a stupid question, but is it possible to quantify just how much more efficient these new architectures are?
It's an excellent question. Can you prove it? If you go to an outside partner and you say, we have this crazy idea that may be worth pursuing, they say, well, go ahead and pursue that and let us know when you have some confidence that it'll work. I can provide you with a paper right now for the photonic computer that I talked about earlier that could replace a GPU and how much more efficient it is than a GPU. And so that paper will show that it's roughly 2x more efficient than a GPU. And it's especially useful for signals that are already in an optical format. And so using photonics to move information from point A to point B, if it's already in photonic form, why convert it back into electrons and use a GPU? Why not implement an optical GPU? And so that was the inspiration for using this approach. And we did publish a paper that showed it would be much more efficient. And now we are actually building a very small version of it to prove that what we wrote in that paper is in fact correct. And we aren't just making it up.
Ray, why should our listeners be paying attention to novel accelerators?
5 years ago, I thought the role of machine learning and even AI in science was going to be limited. And I was absolutely wrong about that and not ashamed to admit it. And so the reason that your listeners should care is that right now, generative AI and accelerators for solving difficult problems, they're at the threshold, at the forefront of being able to help with these major advances. And the world could change in really significant ways. In medicine, in materials, in energy, in information technology. It will have a huge impact on our lives. And it will be because we have figured out how to harness these systems, not to replace us, but to help us.
Thanks so much, Ray. And you can find more on the topics discussed in today's episode in the show notes. Incidentally, we'll be welcoming Ray back next week to talk about physics-based AI. So do come back for that one. Should be a good one.
Yes.
All right. Well, we're getting towards the end of the show, and you know what this means. It's time for This Week in History, a look at monumental events in the world of business and technology, which has changed our lives. And it's not about Mayo.
No, it's not about Mayo. And I don't know if you remember, Aubrey, but the clue last week was it's 1911 and we're heading around the world in 17 minutes. And I had no idea what it was. I think I said something along the lines of, that's definitely slower than the speed of light. But anyway, it was, of course, the first ever test of how quickly a telegram could be sent around the world this week. 113 years ago.
Wow.
Now, the experiment was conducted by a New York newspaper who transmitted a message simply saying, this message was sent around the world at around 7 p.m. It traveled over 28,000 miles and was relayed by 16 operators globally before arriving back at the office from which it was sent 16 minutes and 30 seconds later. I mean, 70 minutes is not a lot of time, is it?
No,
to go around
it's
the
not.
world. Anyway, all of that stuff is absolutely fascinating and amazing and helps you to really appreciate the sort of technology we have today. Aubrey, we are talking to each other across the Atlantic. I know I've said it so many times, but it blows my mind how far away we are from each other, and we are literally speaking instantaneously. Right. What's the clue for next week, Aubrey?
Okay, so the clue next week is it's 1831, and this bright spark really got us moving. Do you think you know what it is?
Oh. I think I do. I'm not going to say it. I don't want to spoil it for listeners, but I think I do.
Well, tune in next week to find out if you're right. And that brings us to the end of Technology Now for this week. Thank you so much to our guest, Ray Beausoleil, Senior Fellow and Senior Vice President at HPE and leader of the Large-Scale Integrated Photonics Lab at Hewlett Packard Labs. And to you, our listeners, thank you so much for joining us.
Technology Now is hosted by Aubrey Lovell and myself, Michael Bird. And this episode was produced by Sam Datta-Paulin with production support from Harry Morton, Zoe Anderson, Alicia Kempson, Alison Paisley, Alyssa Mitri, and Camilla Patel.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, Katie Guarino, and our social media designers are Alejandra Garcia, Carlos Alberto Suarez, and Ambar Maldonado.
Technology Now is a Lower Street production for Hewlett Packard Enterprise, and we'll see you at the same time, the same place next week. Cheers!